Welcome to my talk. We are talking about Spectre, but also Prefetch, Meltdown, and Foreshadow a bit. And we will start right away. And I will start with a statement that we heard in January 2018 about Meltdown and Spectre. And that was from Intel. And Intel basically said, Meltdown and Spectre can only leak from L1. And here's the first task I have for you today. It's go to this link. I have a quick poll, and I want to know from you, do you believe Intel's statement? Meltdown and Spectre can only leak from L1. Okay, let's see. I know. Some people are saying yes, okay. I will have a few more questions, so if you join later on, you can stick other questions. But let me skip ahead, and I will just go to the next statement. And this is from the Foreshadow paper. And the Foreshadow paper discovered that there's a difference between Meltdown and Foreshadow. So for Meltdown, when you try to leak data that is not in the L1 cache, it actually succeeds. It doesn't work as well as if it's in the L1 cache, but if it's in the L2 or L3 cache, or even in the main memory, it still succeeds sometimes. Foreshadow, there they reported, it never works. So this is interesting. So are you really sure about this? Question. Another thing that we observed when we worked on the Meltdown attack was that prefetching improves the Meltdown attack. So if prefetching improves the Meltdown attack, maybe we can use that somehow. So let's take a look at this effect. So we have our operating system with user space, non-canonical space here, kernel space, and then in the kernel space, there's the direct physical map. That's a region in memory that directly maps the entire physical memory into the virtual address space, into the virtual address space of every process. The prefetch side channel that we discovered in 2016 works like this. And this is just the address translation attack from the prefetch side channel paper. There's a second attack in there, which works exactly as described in the paper. So this one is described in the paper, and it also works. You can reproduce this. It works like this. You take the direct physical map address, you flush an address I, which might be the corresponding user space address. Then you prefetch the direct physical map address, which shouldn't work, right? Because this is in the kernel space. User space programs are not allowed to do that. Then you yield a bit, and maybe there's some theory behind that, why we need this yield here. And then we perform an M-access to this address again, right? That we just flushed. And what do we observe? So we first flush it, then we prefetch it, then it's in the cache again, and then we observe the cache hit. And this only works if I is the address that corresponds to this direct physical map address, and with that, you can directly retrieve the physical address for any virtual address in your user space program. Pretty nice, pretty strong oracle, and we came up with a defense against that, and that was the Kaiser mitigation and prefetch side channel, but also other attacks. And we tried that, and we ran this exact same binary for the prefetch side channel attack, once with the patched kernel and once with the unpatched kernel. And here you can see that in the unpatched case, it leaks, and in the patched case, nothing. So it really, really works well. So we tried this again with KPTI in 2018 after these patches went into the mainstream Linux kernel. So this is March 2018, February 2018. Actually, we saw this for the first time when we were at Israel. So what we observed, there's still leakage. So this attack still works. Interesting. Yeah. Okay, so maybe the Kaiser paper was wrong. So let's take a look at the prefetch paper to investigate where the error could be. This is the basic attack algorithm. 3 times you have to do the following. ASM volatile prefetch, this is a prefetch instruction with the direct physical map address, and then get yield. You have to do this exactly 3 times, and then it works. Okay, now I want to know from you, maybe we can do a bit of a brainstorming here. Yes, how can I test this hypothesis? Prefetch prefetches kernel memory into the cache. You've just seen the code on the previous slide. It was this code here. How can I test the hypothesis? Maybe you have a comment that you can leave me here on the Menti, just some suggestion what I should try to make sure that it's really the prefetch that is responsible for this effect. I'm waiting for some responses. Any responses? You can also write it in the chat, but then I can't see it, right? Here. So what I thought back then, there's also, try another instruction instead of prefetch. Yes, try another instruction. Or what if I just omit this entire prefetch instruction? If I don't do it, if I comment it out. Right? So we did that. We went through the code line by line and checked whether any part can be omitted. So let me go back to the empty slide so that I can show you this. So we tried this. We changed this to 2 times, fails. Okay, that's interesting. Changed it to 4 times, also failed. We removed this part, also failed. We also, maybe another poll here. So we remove this entire line and maybe another poll here, because now we remove the prefetch. Can we conclude that prefetch is necessary, or is prefetch necessary? Yes, no, maybe. That doesn't seem to be very clear, right? And now a lot of people say no, also because we by now also know that it's not necessary. But let me just continue here with this next slide. When we remove the get yield, it also doesn't work, right? So our conclusions at the time were that prefetch is necessary and get yield is also necessary. And that was quite logical, actually, because when you remove the prefetch, then there's nothing that would cause the prefetch effect. And if you remove the get yield, then maybe the CPU is too busy, because if you yield, then you would also run into the situation where the scheduler would use a halt instruction, say, well, I don't need time now, so let's just halt the CPU, let's idle the CPU. So the CPU might use these idle cycles to perform these prefetches. Maybe these prefetches, after all, will be executed in the regular out-of-order execution pipeline. They are regular loads, basically. Okay, so this sort of makes sense that you have to give the CPU some time to react to the prefetch. Our conclusion was yield is necessary, prefetch is necessary. And then we also tested what if we pass the wrong address here? It's also important. If we pass the wrong address here, then it also fails, right? So this is more indication that this is actually necessary as is. So passing the right address, and we analyzed the prefetch paper in hindsight and identified that we made the following hypothesis. The prefetch instruction is necessary. It is necessary to place the value in the register that is used by the prefetch instruction, the address that you want to fetch. The get yield is necessary. You have to use the user space accessible bit. It doesn't work if you use the present bit, for instance. That's not present. That's what the Kaiser paper then uses. And it only works on Intel CPU. We haven't observed this effect on other CPUs. So this is interesting. But why does it still work with KPTI then? So we tried something that someone earlier already suggested. We replaced this with not. And in earlier experiments, we didn't get this to work. But the change that we now made was basically placing this direct physical map address in more different registers. And it works. So this was quite shocking. So what we then did was we just placed the DPM address in basically all the registers without running any ASM instruction corresponding to that, and it works even better. So this is nice. So we were like, okay, maybe we misunderstood this effect, and this is fine. This is research, right? We are discovering something. We come up with a good explanation, try different things to check whether the hypothesis makes sense. It makes sense, and later on we discover there's an underlying effect that is more complex that we didn't understand. So what we then thought, well, maybe this is a new hardware prefetcher, and it somehow dereferences registers just like that. Maybe speculative dereferencing. So we disabled all the prefetches. It still works. So we can conclude that documented prefetches are not required for the address translation. But it could still be in undocumented. So what we did was we changed this to instruction pointer relative addresses, and then it fails. Interesting. So this is interesting, but it still doesn't tell us much about the hypothetical register prefetcher. It could still be a hypothetical register prefetcher, but it gets less likely. Then we conclude here that the reference location will only be fetched into the cache if the absolute virtual address is stored in one of these registers. This is interesting. The absolute virtual address is stored in one of these registers. Think about Foreshadow. What is the meaning of a virtual address there, and can it be fetched? So this gets this leads to interesting implications on the Foreshadow attack. Let's continue. We also replaced the get yield system call then with a different system call, right? It still works. In some cases, it even works better. So we conclude that the essential part is performing syscalls or interrupts while specific registers are filled with attacker-chosen addresses. And this already points us into the direction of the kernel. But the problem is when we do this research, it's pretty much like this, right? We don't know what's left or right of us. We just see, oh, there's an effect that works. If we remove this line, it doesn't work anymore, so this line must be responsible. So we made further changes. We changed the user accessible bit from 0. So we left this and used instead the present bit and set this to 0. So this is not present in this process anymore. This page, it's not just kernel mode. It's not just the kernel page, but it's not there anymore. But how can you then test whether the effect still works via a second process? Because this direct physical map is present in all the processes, right? So in one of them, we set this page to not present. And what do we observe? No leakage. So this is very interesting. So that means that the effect adheres to kernel semantics. And we also later on observed that it also, we can't just fetch arbitrary user space addresses with this effect into the cache. So it adheres to snap. So what we can conclude here is it must be something that is code execution in the kernel. And then we also observed that it also works on AMD, on ARM, on IBM. And what we observed is that any Spectre susceptible CPU is also susceptible to this speculative dereferencing type effect. And we were like, oh, this in 2016 that we exploited there was actually not the prefetch instruction, but it was a Spectre. Okay, so let's see what kind of Spectre gadget this might be. For instance, you might have a definition like this, where you have some math functions that take either single or false, and then the right math function will be called. So you have some form. You could also have this in C++ with class hierarchy, but in the kernel, more likely you have some function pointer table. For instance, for system calls, you would have a function pointer table. And after this misprediction into one of these branches here, you would find that there are array accesses there that dereference, for instance, these pointers that are passed into these functions. An example could be, for instance, a function where you pass a pointer into the kernel versus a function where you pass no pointer into the kernel, and therefore the register is not overwritten. And when you mispredict into the wrong path, then this register might be used, although it has not been overwritten with what the kernel should write there. Okay, so in the speculative execution case, this goes wrong then. Okay. Yeah, so we found a Spectre BTB gadget in the kernel that actually was responsible for the leakage that we saw, or for most of the leakage that we saw. Actually, it was not possible to pin it down to exactly one gadget because there were multiple gadgets that contributed to the and for instance, could previous task fair dereferences user controlled register speculatively. There are more gadgets also in NVMe interrupt. So if you have an NVMe disk, and you might just have this type of effect without system calls, just by having interrupts from the NVMe disk. So how does it then work actually? So we have our DPM addresses now in all the registers. And when we fill these registers, afterwards we, on the system call or an interrupt in the kernel, you will have this indirect jump, and it predicts the wrong handler. This wrong handler dereferences the address, and by that fetches the cache line into the cache. And now we understand the root cause of this. And this has implications, right? Let's take a look at Foreshadow or L1. This was claimed that it can only leak data from L1. And what it exploited was this present bit. In the page table entry, the present bit had to be set to 0. And in that case, it would fetch the wrong data. So let's take a look at this in more detail. So we have the present bit that is passed to the guest physical to host physical address translation. And then you perform a memory lookup and get the data from the L1. And then you, because you don't want to access the physical page every time, so you fetch it from the L1 instead. And this is looked up with the physical address. Now, what happens if the page is not present in the Foreshadow case? In that case, we skip this part. We don't perform this guest physical to host physical translation because it's not valid. Not present, it's not valid. And that means we directly, and this is a flaw in the CPU, directly look up the L1 with actually not really the virtual address, but more the physical address that is stored in this page table entry. So with Foreshadow, you would normally modify a PTE such that you read the host physical memory, and it's mitigated by L1 flushes. And the KVM default is that you conditionally flush the L1. But with speculative dereferences, we can fetch data from L3 to L1 in the hypervisor mode by using such a gadget in the KVM hypervisor. And we just have to fill our register set with addresses that are valid in the hypervisor, and that in the hypervisor map to exactly the same as the data. And with that, Foreshadow is still possible. And that's, of course, that was a bit unexpected that we can do this. But you see there's a connection between all these effects. And so we revive Foreshadow. Let's take a closer look at that. So we perform a hypercall or an interrupt with this virtual address, and the hypervisor will then fetch this into the cache. And afterwards, we can perform Foreshadow on this physical address. And here I have a live demo. It's not live, it's pre-recorded by one of my PhD students. And here we have some program that shows us some physical memory and a physical address. And we will now leak this physical memory from the host in a virtual machine. Right? Demo. Yeah, let's first schedule the right course, because Foreshadow only works in a cross hyperthread scenario. We pin them to the same course. We maybe cause some stress just to have some more activity. We found that this helps a lot with various microarchitectural attacks, especially the interrupts that we use here. They will cause NVMe interrupts. So this is very nice, so that we can then leak the data. And now the attack is running here in the virtual machine. You can see that it's slowly, byte by byte, from physical memory of the host. Okay. So, thank you for the applause. Maybe we should think about that a bit more. What if the value is not an address? So this effect works just by loading things into registers, and suddenly they end up in the cache without us doing anything. What if it's not an address? Well, we can leak these register values by just acting as if they were addresses. Let's think about a scenario where, for instance, we have a speculative dereference in SGX. We can't read the register values from SGX, but what we can do is we can map the entire virtual address space that is 48 bits in size. And now many values are addresses because we cover 48 bits of the address space. This works great for 32-bit registers because they all map into a very low part of this 48-bit address space. And then we can perform a binary search where one half of the pages maps to one physical page and the other maps to another physical. And then we just use flush and reload to determine which of the two it is. And with that, we can recover bit by bit this register value. We illustrate it pretty much like this. So you have a physical page, half of the pages are mapping to this one, half of the pages are mapping to this one, and then you have to change these mappings over time so that you can determine the exact value. Yeah, this works very well. The register part, the register part even works in browsers, but it's very slow. But we have these NVMe interrupts. It's very slow, 1 cache fetch per minute, super slow. But if we don't have these NVMe interrupts, it's even worse, then we have 2 cache fetches per hour. Yeah, there's just not a lot of this these register dereferences anymore in the kernel, because the kernel also got Spectre mitigations. Yeah, so Kaiser, this is also an insight. Kaiser does not prevent the address translation attack, although I would say we did what we were supposed to do at the time. We tested whether the exact same attack binary and even modified variants of the binary work under the old and the new kernel, and it didn't work anymore. And the question is, why was that? Why did it not work anymore? Why did the attack not work anymore? And the reason is that depending on the kernel version, and when you recompile the kernel, the exact registers that will be dereferenced change. And this might, in some cases, be registers that are rarely used when you compile a user space program. Even with multiple registers used in inline assembly, there is a larger number of registers. And before you understand that this is actually an effect coming from the kernel, there would be no reason to fill all the registers with these values. So at the time, it totally makes sense to test whether the effect goes away with the patched kernel, with the same binary, and with slight variations. And if you can't get it to work anymore, then you can conclude that very likely your patch mitigates it. But it also shows how incomplete science naturally is. This is natural science, and it will never be complete. We will never be able to prove absolutely that an effect comes from this or that, because if you take into account the physical world, for instance, Rowhammer plays into this digital world and changes how these things behave, even if we formally defined them and implemented them exactly as defined. And also, these things are getting more and more complex, so it will be more and more difficult to actually reason about the system without making simplifications. And with that, you get the same problems as with natural sciences, where we also simplify how nature works. We also discovered that IDRS is vulnerable. On Ice Lake, we get 30 bytes per second of leakage, and the full Spectre BTB mitigations are required even on Ice Lake. where EIBRS is available, but you still have to use the full mitigations with red line and all the other features that are implemented. The conclusion is root cause analysis is difficult. I mean, this is science. It's never easy, but if you don't know what the system does, then it's a lot more difficult. Speculative execution is the actual root cause, not Prefetch. Prefetch actually has nothing to do with this attack. In the Prefetch attack paper, in the Prefetch sidechain attack paper, there's actually a second attack that does work by timing the Prefetch instruction, and that is definitely depending on the Prefetch instruction. So it was just one of the two attacks that we misunderstood at the time. And this led us to wrong security assumptions about the Kaiser patch. So this was designed under a wrong security assumption. Maybe we wouldn't have written that if we would have figured out that it doesn't work earlier on. L1TF still works. You can leak values directly. This is also a new insight that we found here, that Spectre is not just helpful for observing memory fetches of another program, but also that you can directly values through this dereferencing effect. Side channels work, the Prefetch sidechain works on browsers and also on non-Intel CPUs alike. So we still need mitigations also now on non-Intel CPUs. And with that, I'm at the end of my talk, and I see there is one question on Menti, and I will check that immediately. Let's see the Q&A. And we have, could the SCAD yield cause the kernel page table to be loaded? The SCAD yield is also not necessary here. And the kernel page table would also, most of the time, the relevant entries of the kernel page table would be in the cache and in the TLP as well. Does the address translation attack work on the latest kernel version? And why the attack works when the loop runs 3 times while 4 and 2 times fails? Oh yes, this is also very interesting. So I haven't tried it on the latest kernel version. There are coming updates all the time. But at the time of writing, it was working on the most recent kernel version if you disabled the Spectre v2 mitigations. With the Spectre v2 mitigations, we don't get leakage anymore because red line is used, and then indirect jumps in the kernel don't occur anymore. Why does the attack work when the loop runs 3 times while 4 and 2 times fails? Yes, this was very, very odd when we were working on this, because it was super fragile, and then it works with 3, with 4 it doesn't work, with 2 it doesn't work, with any other number that we tried it didn't work as well as with 3. And the reason very likely was that with 3 times, the compiler will do loop unrolling and fill one register with this variable, and it will be different register with 2 or 4 or any other number that we tried. And if the register fits very well to the kernel that we compiled, right, both of them have to use exactly the same register if you're only filling one register. Then in this case, you would not see the leak if it uses the wrong register. So this is the likely explanation for that.